So let's suppose for our example, a equals 2, -1, -1, 2, with an x0 equaling 3, 1, which represents our initial state, maybe for our system. And we want to find the kth term. So let's do this generally first, and then we'll use our specific case. So let's just write out initially what each one of these looks like. Again, x1 is equal to a times x0 using our difference equation. x2 is equal to a times x1. However, x1 we can describe in terms of x0. So it's a times x0, or a squared times x0. x3 is equal to a times x2, which is equal to a times x2, but x2 is a squared times x0. So this is a squared rather times x0, which is a cubed times x0. X to the fourth, or x sub 4 rather, is going to be equal to a times x sub 3. But again, if we use our replacement, we get a times a cubed x sub 0, or a to the fourth x sub 0. I think we can see the pattern here, hopefully. And if we were to continue this on down, the kth term would be equal to, you'll notice here we've got x sub 4, a to the fourth, x sub 3, a cubed, x sub 2, a squared. So our pattern is a to the k, x sub 0. So that we need to figure out. Well, we could use the diagonalization from our previous lesson, but it actually turns out to be more work than we actually have to do. There's a theorem 11 that we can grab from 4.4. And what this theorem says is the following. If AU is equal to lambda u, then a to the k times u is equal to lambda to the k times u. And this is specific to the fact that u is the eigenvector for the lambda that's given. So if we assume A is non-defective, then we get n linearly independent vectors that can serve as a basis for all of Rn. This was a result that we had from our work with non-defective matrices. Then we can say the following. x0 can be written as a linear combination of those vectors. So u1 plus some coefficient or scalar a2, u2 plus ... an u sub n, where u sub 1 to u sub n are the eigenvectors of A. So then we can take our equation that we had up here, this x sub k being equal to a to the k x sub 0, and we can go ahead and make that replacement now that x sub 0 is a linear combination of the eigenvectors of A, and get that x sub k is going to be equal to a to the k, again, times x sub 0, but we're going to make that replacement on the right side. This is going to be a to the k times a sub 1, u sub 1, plus ... plus a sub n, u sub n. And that's going to be equal to a sub 1, a to the k u sub 1, plus ... a sub n times a to the k u sub n, just using our distribution of our matrices there. And again, noting that our rule says that we can replace a to the k with lambda to the k, where lambda is the eigenvalue associated with a particular eigenvector, we get the following. This is now equal to a sub 1 lambda sub 1 to the k u sub 1 plus dot 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 plus a sub n lambda sub n to the k u sub n. And the advantage here is that computing a to the k may take a while, depending on how large the matrix A is, whereas computing lambda to the k, lambda of course just being a scalar, we can quickly compute that value to a kth power without a lot of effort. So this gives us a really nice formula then for computing the kth value or kth term of the sequence when we go through and run the iterations of the difference equation. So now let's look at it for our particular example. So we had that A was equal to 2, -1, -1, 2. Again, x0 was equal to 3, 1. And I've gone through and made some of these calculations already, so I'll jump to the characteristic polynomial here, which ends up looking like 3 minus 4t plus t squared. Of course, this will factor here into 3 minus t and 1 minus t. And of course, we want to solve where that's equal to 0. So we get a couple of eigenvalues, lambda being equal to 3 and 1. And we can go through and find the associated eigenvectors for those. Again, the eigenvalues, or the eigenvectors rather, for, say, lambda sub 1 equals 3 is going to be equal to -1, 1. And for lambda 2 equaling 1, we get an eigenvector of 1, 1. So that means we can rewrite x sub 0 as a linear combination of those two vectors, which will require us to find a couple of coefficients. So we want x0 to be equal to a1 times -1, 1 plus a2 times 1, 1. And we could probably do this by inspection, but of course we can also go ahead and make an augmented matrix out of this and just solve it. -1, 1 and 1, 1, and we want the solutions here. And when you do that, you end up with a couple of constants out of it. This will tell us that a1 is going to be equal to -1, and a2 is going to be equal to 2. That's not a good looking 2, so let's fix that up. So that means that x0 is equal to -1 times -1, 1 plus 2 times 1, 1, and we could verify that that's in fact correct. So now we can set up the rest of our equation here. It says that x sub k is going to be equal to a1 lambda 1 to the k u sub 1 plus a2 lambda sub 2 to the k times u sub 2. So starting to plug in all those values, we had a1 was -1. We have that the eigenvector and eigenvalues, lambda 1, were 3 and -1, 1. So we can plug those in. Plus a2, which is 2. times the eigenvalue lambda sub 2, which was 1. We raise that to the kth power. And then u sub 2, the second eigenvector associated with lambda equals 1, was 1, 1. So this becomes the general formula then for the vector x sub k. And if we go ahead and kind of clean that up a little bit, what we end up with is something that looks like 2u sub 2 minus 3 to the k u sub 2, or sorry, rather u sub 1. Or if we combine this all together and write it out as a vector, we get x sub k being equal to the vector 2 plus 3 to the k and 2 minus 3 to the k. And this, if we let k go to infinity, then is divergent. Just using our general understanding of sequences from third quarter calculus. So if you want to see an example where the situation ends up being convergent, you could look in the text at example number 3, and this will give you that kind of a case. If you want to see all types of solutions, you can investigate that on page 343 and 344 for more solution types out of these. But at this point, the big goal is to try and figure out how to come up with this general term here for the kth value and just let that thing go to infinity to see whether or not it's convergent or divergent.